Welcome to another module in this massive open online course on estimation for wireless communications. So, currently we are looking at intersymbol interference in wireless communications, right, and equalization to remove the intersymbol interference. We have looked at the least squares principle for equalizer design, right. So, today let us look at a simple example for equalizer design in a wireless communication channel with intersymbol interference. So, we are looking currently we are looking at channel equalization, and channel equalization, as you know, is done for ISI removal, that is to remove the intersymbol, where ISI stands for the intersymbol interference, correct. So, today let us look at a simple example for channel equalization. So, in this module we want to look at a simple example for channel equalization. So, consider an intersymbol interference channel with two channel taps. Consider an ISI channel with L equal to L equal to 2 channel taps, correct. All right. So, we said in the equalization model, that is in the model with intersymbol interference, we are denoting the number of channel taps by capital L, and these channel taps are denoted by the actual channel coefficients, or the channel taps are denoted by H0, H1 up to HL minus 1. So, we have L equal to 2 channel taps, that is H0 and H1. Okay. So, we have 2 channel taps, that is H0 comma H1. Further, let H0 equals 1 and H1 equal to 0.5, right, and therefore, now our system model, our received symbol Yk equals, remember, H0 times xk plus H1 times xk minus 1 plus Vk, and now we let us substitute the values for H0. So, this and H1, and this gives me Yk equals 1 times xk, since H0 equals 1, plus 0.5 times xk minus 1 plus Vk, which is basically, we have Yk equals, therefore, xk plus 0.5 times xk minus 1 plus Vk. This is the model for the received symbol Yk, in which, remember, Yk is the received symbol at time k, xk is the transmitted symbol at current time instant k, xk minus 1 is the previous transmitted symbol, that is the transmitted symbol at the previous time instant k minus 1, which is interfering with the current symbol xk, that is the current transmitted symbol xk, and Vk is the noise in the channel. Okay. So, let me just rewrite those, that is Yk is the received symbol this is the transmitted symbol xk minus 1, this is the transmitter symbol at k minus 1, at time k minus 1, and Vk is the noise. Therefore, xk minus 1 is interfering. What we have is basically we have xk minus 1 is interfering with xk, that is xk minus 1 is interfering with the detection of xk minus 1 is interfering and this is termed as ISI or inter-symbol interference. That is this wireless channel in which yk, in yk, that is we have xk as well as xk minus 1, which is interfering with the previous symbol xk minus 1, which is interfering with the current symbol xk. This is termed as inter-symbol interference, and removal of this inter-symbol, the process of removal of this inter-symbol interference is termed as equalization. So, we perform equalization at the receiver to remove the effect of ISI. Okay. All right. So, now consider an R equal to 3 tap equalizer again. R equal to 3 tap equalizer based on the received samples yk plus 1 or based on the received samples yk plus 2, yk plus 1 and yk. So, we have 3 samples, and basically using this we want to design an R equal to 3 tap equalizer, correct. So, now let us write the equations for these symbols yk plus 2, yk plus 1 and yk. I have yk equals xk plus 0.5 times the previous symbol xk minus 1 plus Vk, right. Similarly, yk plus 1 equals the current symbol xk plus 1 plus 0.5 times the previous symbol to xk minus 1, that is xk at time instant k plus Vk plus 1 and yk plus 2 equals xk plus 2 plus 0.5 times xk plus 1 plus Vk plus 2, correct. Now, let us write this as a matrix. Now, if I write this as a matrix, I have, so writing as a vector, I have yk plus 2, yk plus 1, yk, which is equal to 1.5 0 0 0 1 0.5 0 0 0 1 and 0.5. This is the same as the matrix H that we have written in the previous module, except now I am substituting for the channel coefficients H0 and H1. This is the matrix H times xk plus 2, xk plus 1, xk x k minus 1 plus we have the noise vector, that is V k plus 2, V k plus 1 and V k, and we said this is the received vector y bar of k, this is the transmitted vector, this is x bar of k, this is the noise vector v bar of k, and basically using this now we can model the we can develop the vector, basically write the vector model for this intersymbol interference channel as y bar k equals h times x bar k plus v bar k, where v bar k is the noise vector, correct. So, therefore, I can write this as y bar k equals h times x bar k plus v bar k, where v bar k is the noise vector. Remember, this is an R cross 1 matrix, R equals 3. So, this is basically a 3 cross 1 matrix. H is an R cross R plus L minus 1 matrix, R equals 3, L equals 2. So, this is a 3 cross 4 matrix, this is x bar k, which is R plus L minus 1 cross 1, this is 4 cross 1, and this is an R cross 1 vector, which is a 3 cross 1 noise vector. So, basically what we have done is we have developed this model, that is y bar k equals h times x bar k plus v bar k for this ISI, the intersymbol interference, to basically capture the effect of this intersymbol interference in this wireless channel. And now let us design our R equal to 3 tap equalizer. Okay. So, we are going to design the 3 tap equalizer to remove the effect of intersymbol interference in this wireless channel, correct, and let us denote the 3 taps by the coefficient C0, C1, C2. So, basically now let the coefficients or taps of equalizer these are the 3 taps of the equalizer. So, we have R equal to we have R equal to 3 taps, and therefore, now I can write the equalizer, that is equalized symbol x k equals C 0 times y k plus 2 plus C 1 times y k plus 1 plus C 2 times y k. That is, I am estimating the symbol x k, that is x hat k is the estimate of the symbol x k after removing the interference from the other symbols, that is x k plus 2, x k plus 1 and x k minus 1, and that estimate is given by the linear combination of the output symbols y k plus 2, y k plus 1, y k as C 0 times y k plus 2 plus C 1 times y k plus 1 plus C naught times y k, which now I can write as basically the row vector C 0, C 1, C 2 times the column vector y k plus 2, y k plus 1, y k. This is the transpose of the equalizer vector C bar, this is C bar transpose, this is y bar k. So, the equalized symbol x hat k equals C bar transpose y bar k, and now substituting the expression for y bar k, which is equal to h times x bar k plus v bar k, which can be now by removing the brackets I have C bar transpose h times x bar k plus C bar transpose V bar k, and now we said to achieve equalization this vector C bar transpose H, this vector for perfect equalization ideally this should be the vector 0 0 1 0, alright. If it is not exactly 0 0 1 0, we would like to at least approximate the vector 0 0 1 0 as closely as possible, so that it picks the vector picks xk while it nulls the other symbols xk plus 2, xk plus 1 and xk minus 1, and that is the basic idea in this equalizer design. This is therefore known as also the zero forcing equalizer, zero forcing criterion for equalizer design, because you are forcing the interference from the other symbols xk plus 2, xk plus 1 and xk minus 1 to 0, and therefore this can now be expressed as I have to have C bar transpose H, this vector should basically be as close an approximation as possible to 0, which means if I now take the transpose, so taking transpose, I have this should be equal to H transpose times C bar, or basically should be as close as possible to H transpose times C bar, and H transpose is, remember the matrix, it is the transpose of H, which is 1, 0.5, 0 0, 0 1, 0.5, 0, 0 0 1, 0.5 times C bar, and this basically we said is our matrix H transpose. This is the matrix 1 bar 2 with zeros everywhere and 1 in the second position. So, this has 0 in the 0th position, in the first position, 1 in the second position and again 0 everywhere. So, 1 bar 2 is basically the vector which has 1 in the second position, start counting from 0, 1 in the second position and zeros everywhere. And therefore, now the least squares criterion for equalizer design can be expressed as, in fact the least squares criterion for zero forcing equalizer design, let us for zero forcing or ZF equalizer design, for zero forcing equalizer design is minimize norm 1 bar 2 minus H transpose C bar square, and the equalizer C bar, the least squares basically solution for the above this thing, the equalizer C bar is basically given as H, this is something that we have seen before, H transpose inverse times H into the vector 1 bar 2. And remember, that is because this is basically because H transpose, the matrix H transpose is a 4 cross 3 matrix, and therefore, it has more rows than columns. If you look at the matrix H transpose, it is a 4 cross 3 matrix. So, the matrix H transpose is a 4 cross 3 matrix. Therefore, if you look at this system of equations 1 bar 2 equals H transpose times C bar, that is an overdetermined system, alright. So, that is an overdetermined system. So, one can solve it such as, one cannot solve it exactly, one can solve it only to minimize the error between 1 bar, this vector 1 bar 2 and H transpose C bar, that is the least square solution C bar. In fact, this is similar, remember yesterday we said this is similar to the multiple antenna downlink channel estimation, where we have Y bar equals X times H bar, and X is the pilot matrix which has more rows than columns, and colloquially this is also known as a tall matrix, since basically it has a structure that appears tall, that is it has more rows than columns. If it is an M cross N matrix, there basically, or it is an N cross M matrix, where N, the number of observations, is more than M, the number of antennas in the context of channel estimation. That is what we have seen previously. Anyway, coming back now to our equalization problem. So, now the equalizer can be designed by substituting these matrices H and 1 bar 2. So, now let us look at our matrix, let us look at this product H transpose, this product H transpose. Now, let us substitute the expression for H. This expression for H is given as 1.500001.500001. times the matrix H transpose, and the matrix H transpose is 1.500001.5. This is my matrix H, this is my matrix H transpose, and you can see, you can compute this, you can evaluate this, and you can see H transpose is given as 1.25, 0.50, 0.5, 1.25, 0.5, and again 0, 0.5, 1.25, and basically just writing this as fractions for convenience, I have, well, 5 by 4, this is half, 0.50, this is half, 5 by 4, this is half, 0, half, 5 by 4, this is my matrix H transpose. So, basically substituting the values. So, substituting the matrix H, I have basically evaluated H transpose. Now, we have to evaluate H transpose inverse, and to evaluate H transpose inverse, first we have to evaluate the determinant of H transpose. Okay. So, the determinant of H transpose, let me write it this way, that is simply denoting this by the determinant. This is basically the determinant of H transpose, and you can calculate this, you can evaluate this, you can see this is 5 by 4 times 25 by 16, this product minus this product, 25 by 16 minus 1 by 4 plus half into, well, this product minus this product, that is minus 5 by 8, that is basically 5 by 4 into 21 by 16 minus 5 by 16, which is equal to, well, that is basically 105 minus 20 divided by 64, which is basically, you can again check this, this is 85 divided by 64, that is the determinant. We have evaluated the determinant of this matrix H transpose. Now, to evaluate the inverse, again you should be familiar with the evaluation of the inverse of a simple 3 cross 3 matrix. Basically, I have to replace each element by the cofactor of the transpose. Yeah. So, if in case you are not familiar, you can look up the procedure. It is a very simple procedure where I am replacing each element by the cofactor of the element, corresponding element in the transpose. Yeah. So, therefore, H transpose can now be computed as H transpose is 1 over the determinant, that is 1 over the determinant times this matrix of cofactors, which is given as 21 by 16 minus 5 by 8, 1 by 4 minus 5 by 8, 25 by 16 minus 5 by 8, 1 by 4 minus 5 by 8, 21 by 16. And basically, if you look at this, the cofactor is very simple. For instance, the cofactor of this element, we have already evaluated that cofactor of 5 by 4, the cofactor of this element is basically 5 by 4 times 5 by 4 minus, that is 5 by 4 times 5 by 4 minus 1 by 4 equals 21 by 16 and so on. So, this is basically you can look it up, this is the matrix of cofactors, can be found in any standard textbook on linear algebra. And now, taking the factor of 64 inside, this is basically you can further simplify this as 1 over 85 times 84 minus 40 and 16 minus 40 100 minus 40 16 minus 40 and 84. And now, therefore, this is what is this? This is basically H transpose inverse. So, this is basically H transpose inverse. So, we have evaluated H transpose inverse. Remember, the equalizer is H transpose inverse times H into 1 bar 2. So, I have to evaluate this other component, that is H into 1 bar 2, and that is very simple. That can be evaluated as H into this vector 1 bar 2 is basically your matrix 1 0.5 0 0 0 1 0.5 0 0 0 1 0.5 times this is the vector 1 bar 2, that is 0 0 1 0. So, this is basically your H transpose, this is basically your vector 1 bar 2. So, this is equal to, and look at this 1 bar 2, this simply picks the second column, that is start counting from 0, this simply picks this column and you can multiply this, that is simply your 0.51, or in other words that is basically your 0.5 comma 0.5 comma 1. Therefore, the equalizer C bar is the equalizer C bar is now C bar equals H transpose inverse times H into this matrix 1 bar 2. We have computed both these quantities above. H transpose inverse is 1 over 85 times 84 minus 40 16 minus 40 100 minus 40, 16, minus 40, 84 times h 1 bar 2 is 0, half 1, and this when you multiply you can check this, what you will get is 1 over 85 times minus 4, 10, 64, and finally taking this 1 over 85 inside, what I have here is basically C bar, which is equal to minus 4 divided by 85, 10 divided by 85, 64 divided by 85, and this is basically the equalizer. So, what we have done is basically we have evaluated this quantity H transpose inverse times H into this vector 1 bar 2, and that has given us this equalizer C bar. And now what we have to do is basically the symbol x hat k, that is the equalized symbol x hat k can be evaluated as C bar transpose the vector y bar k. That is the last step, that is the implementation of the equalizer. So, x hat k equals C bar transpose y bar k, which is basically equal to your the equalizer which we have evaluated, which is minus 4 by 85, 10 by 85, 64 by 85 times y of k plus 2, or not y bar, y of k plus 2, y of k plus 1, and y of k, and that is basically x hat k, and that shows that x hat k is basically equal to minus 4 by 85 times y of k plus 2 plus 10 by 85 times y of k plus 1 plus 64 by 85 times y of k, and finally therefore, this is basically your equalized symbol. That is x hat k equals minus 4 by 85 y k plus 2 plus 10 by 85 y k plus 1 plus 64 by 85 y k. So, what the equalizer is doing is basically performing a linear combination of the symbols y k plus 1, y k plus 2 to eliminate the intersymbol interference from x k. So, what we have seen in this, basically we have seen a simple example based on L equal to 2 taps, that is a wireless channel model which is intersymbol interference from one previous symbol, that is x k, with intersymbol interference from x k minus 1. We have seen a simple example of this 2 tap intersymbol interference channel, and then subsequently we have demonstrated the procedure to derive an R equal to 3 tap equalizer for this channel. We have evaluated the 3 tap equalizer, and finally also demonstrated how the equalization can be done using this 3 tap equalizer for this wireless channel with intersymbol interference. Alright. So, with this we will stop this module and we will explore other aspects in the subsequent modules. Thank you very much.